Last time we were together, you looked at a beaker filled with strong acid. So you started to figure out what's the concentration of that strong acid by adding some OH minuses. What if what you have in your beaker is not a strong acid, but a weak acid? So here we're going to be using a weak acid. So the weak acid that we will be choosing is acetic acid. This is vinegar. You can use a whole bunch of weak acids. You have your Appendix D. You can pick any one of these. We are going to pick acetic. It is HC2H3O2, and it has a Ka of 1.8, E negative 5. So here we have the pH curve. Oh, first, what are we going to use to add to that weak acid? Well, you have some choices. If it's an acid, then you better use a base because you can't react an acid with an acid, okay? Now, if you want this to react, if you add droplets of weak base, do you think the weak base will extract that H? Okay, you want it to react with that H. You cannot use a weak base because this C2H3O2 wants that H. So you need something stronger to be able to remove that H. So you need a strong base. So every time, whatever your known is, it better be strong. So it can react with whatever is inside your unknown or your analyte. Okay? So here we're going to be using a weak acid as your unknown and using a strong base. The strong base we'll be using is 0.1 molar NaOH. And you have to know the molarity so you can know the molarity of your unknown. So here it is again. On the y-axis you have pH, and on the x-axis we're measuring how much NaOH you are adding. So in the beginning, when you've added 0 NaOH, put a pH probe in there. I forgot to draw the pH probes. Because that's a weak acid, it's going to be a little bit higher than what we started with in the strong acid over here. Of course, it depends on the molarity, but it's not going to be as acidic. So it's going to be, let's say, pH 2 or 3, whatever, maybe around here. We don't know, okay? So let's say it's around 2.5, 2.6, whatever it is, okay? And you haven't added anything yet, and so that's why it's at 0. It is 2.6. Now, let's get ready to add some OH minuses. Okay, when you've added 5 milliliters of OH minus, one of these will cancel. Okay, so what you have left in the beaker is the conjugate base and this acid. Okay, so to get the pH of this, you have to look at what's in the beaker. In the beaker, you have conjugate base and its conjugate acid. To get the pH of this, you can use a pH probe. If you didn't have a pH probe, you can use Henderson-Hasselbalch, okay, where pH is equal to pKa plus log of the base, conjugate base and conjugate acid. So for acetic acid, let's look at Appendix D. It is 1.8 E negative 5. Here I found the Ka. pKa equals negative log Ka. Negative log of 1.8 E negative 5 is 4.74. Please pause the video and verify that. So the pKa is 4.74. 4.74 plus log of the base and the acid. Now let's think about this. You have crossed out one of the H pluses. Now you have this in there and this. And if you've titrated half of it, that means you will have half and half, right? Which means these two are equal to each other. So which means this, let's say it's 0.5, and I don't know what it is, but it's equal. Whatever it is, it's equal. So it'll just cancel each other out. So log of 1 equals to 0. So this whole term is 0. So your pH is 4.74. So when you've added half, if you titrated half of your acid, your pH is 4.74. So it's right here. Okay. So let's keep going. Now I'm going to use this beaker right here because I don't have much room. And I'm going to add more OH minuses. Once I've added 10 milliliters, let's say, then there's 2 of these. This will cancel with this, and this will cancel with this. I have reached what's called, what is it called? Equivalence point, when the moles of acid equals the moles of base. So this is called the equivalence point. Okay. At the equivalence point, what do I have in the beaker? Well, it is that. I have the acetate ion. What do you think will be the pH of the acetate ion? Do you think the pH of this will be pH 7? Okay, well, it's only pH 7 here because the H plus and the OH minus cancel and you have water. But do you have water in this beaker? No, you don't have water. You have the acetate ion. And what that will do is it will hydrolyze, as you already remember from last chapter. This acetate ion will cause trouble. It will hydrolyze in water and produce, the H will go this way, HC2, H3O2, and OH minus. Because your acetate ion hydrolyzed, the hydrolysis is the reaction with water, it produced the OH minus, it caused your solution at equivalence point to be a little bit more basic. So instead of having your pH right at 7, it's going to be a little bit more basic than 7. Let's say 7.5, let's say 8. Okay, so your next dot, it's not going to be right at 7, it'll be around 8. At equivalence point, it is 8. So as you can see, your whole curve is shifted up a bit, right? Where here it's lower, but this one's shifted up. Okay, so this is beaker number 1, beaker number 2, beaker number 3. Sorry, it's all over the place. There's just not much room. And then lastly, beaker number 4. In this beaker, we're going to add a lot more base. So we're going to add 15 milliliters of base, OH minus, OH minus, OH minus. Let's say that's 15 milliliters. This OH minus will cancel this H plus, this OH will cancel this. So what you have left in the beaker is just OH minuses and some conjugate base, which will make, and if you keep adding more, it'll pretty much be the molarity or the pH of a 0.1 molar, which is eventually going to be pH 13. So you're going to eventually go up to all the way here to pH. This is 12, this is 13, all the way here. 15 mils, it'll be pretty much like, it'll start to go up, but eventually you're going to end up at pH 13. So your pH curve looks like this. Maybe I should use a different color here. Okay, so it's going to look like it's going to be pretty flat over here. It's going to go straight up. Until it starts to plateau at pH 15. Okay, so you might be wondering, Ms. Lozano, why is this so flat in here? Because this area is a very special area. This pH is not changing, it's flat. pH is flat, not changing. So what does that mean when your pH is not changing? That means whatever is in there is resisting the change of your pH, right? That means you must have a buffer. Let's see if you have a buffer in there. Well, what is in the beaker here? You have the conjugate base and the conjugate acid. They're weak conjugate acid-base pairs, so that means you have a buffer. So what you have in this region, in this rough area right here, this is called your buffer region. And to get the pH of the buffer region, all you have to do is use Henderson-Hasselbalch. If you have equal amounts, you know, it's easy, but if you have a little bit more of the base than the acid, it's fine. You can still plug it into this formula and you can get the pH of that buffer region. Okay? So, what you have here is the titration of a weak acid using a strong base. The curve looks a little bit different than this. It looks like it's shoot up a little bit. It's a little bit higher because it's not as acidic here. Also, your equivalence point is a little bit higher as well. It's not 7, it's a pH 8 at equivalence point. And the reason that is because you have the hydrolysis of your conjugate base. There's a little bit of OH minus in there that's causing it up. Now, for the indicator, you can still use phenolphthalein because phenolphthalein again changes color around pH 8, so that'll still be fine. So this area could be where your indicator can change color. Okay, and that's it.